Have you ever heard of a PLC or SCADA, DCS, CNC? It kind of sounds like an alphabet soup of tech jargon, right? But believe it or not, this is the secret language that controls pretty much our entire modern world, from the power that keeps your lights on to the factory that actually built the device you're using right now. So today, we're going to decode this hidden language that runs everything behind the scenes.
So, let me ask you this. What do massive power grids, sprawling chemical plants, and super high-tech assembly lines all have in common? Well, the answer is they all run on sophisticated, automated control. Behind every factory floor and every power station, there's this hidden family of industrial computers working tirelessly 24/7 to orchestrate the whole show.
To really get where we are today, we've got to rewind the clock a bit. Before all this sleek automation we see now, the world ran on machinery that was complex, clunky, and honestly super frustrating to work with. Let's take a look.
Okay, so check this out. Before 1968, this is what industrial control looked like. Not some slick computer screen, but these giant walls just packed with thousands of clicking electromechanical relays. Every single one was a physical switch, and together all that clicking and whirring formed the logic that ran a machine.
This setup was, and this is a quote from an engineer at the time, a logistical nightmare. I mean, can you imagine trying to find one faulty switch in a cabinet packed with thousands of identical boxes all clicking away? Every connection was physically hardwired. So, if you wanted to change even a tiny little thing in the process, you had to get the tools out and rewire the entire system. It was slow, unreliable, and just incredibly inflexible.
So yeah, industry desperately needed a better way. And that need, which came specifically from General Motors, led to the birth of our story's hero. A device that would replace these massive relay cabinets and change manufacturing forever. And that hero was the Programmable Logic Controller, or what we all call the PLC. It was conceived by a guy named Dick Morley and his team. And the whole point of the PLC was to be everything those old relay systems were not. It was flexible, it was rugged, it was a solid-state controller that you could reprogram easily. A total game changer.
So here's the core idea, and it's actually pretty simple. Just think of a PLC as a really tough little industrial computer. It senses the world around it through inputs, it thinks by running a program you give it, and then it acts on the world through outputs. It's this powerful little loop. Sense, think, act. Over and over.
Now, let's pop the hood for a second. The whole architecture is modular. Right in the center, you've got the CPU. That's the brain. It uses memory to hold all its instructions. But these I/O modules, they're absolutely critical. They're basically like the ports on your computer, letting the brain connect to all the real-world stuff. The sensors, the motors, the switches.
The human body is actually the perfect way to think about this. The CPU, that's the brain, obviously. The backplane that connects all the modules together, that's like the spine and the nervous system. And those I/O modules we just saw, they're the senses and the muscles, taking in information and making things happen. So how does it do all this so incredibly fast? Well, it uses a continuous loop called a scan cycle. First, it checks all its inputs. What's going on? Then it runs the program you wrote. Next, it updates all the outputs. Time to act. And finally, it does a quick self-check, just some internal housekeeping. This whole loop happens in a few milliseconds. It repeats thousands of times a minute. It's unbelievably fast.
Okay, so PLCs are the undisputed masters of controlling a single machine or process in one place. But what happens when your machine is, say, an entire city's power grid or a gas pipeline that stretches across 3 states? You're going to need a system that can see the whole big picture.
And that's exactly where SCADA comes in. It stands for Supervisory Control and Data Acquisition. And listen, the key word here is supervisory. A SCADA system isn't for high-speed, direct control of a machine. It's all about monitoring and managing assets that are spread out over huge geographic areas. And its architecture really reflects that role. You've got a central control room with what's called a human-machine interface, or HMI. Just think of it as a big, fancy dashboard for the whole system. From there, operators communicate with dozens, maybe hundreds of remote terminal units or RTUs. These RTUs are the boots on the ground stationed way out in the field, collecting data and controlling the local equipment. And you actually see SCADA everywhere, especially in critical infrastructure. It's what manages our power grids, our city water systems, those massive oil pipelines, and even the traffic light network in your town. It gives us that big picture view we need to run these giant, sprawling systems safely and efficiently.
All right, so SCADA is for stuff spread over wide areas. But what about the opposite problem? What if you have an incredibly complex process with thousands of little control loops all happening inside a single site, like a giant oil refinery?
For that challenge, we have the Distributed Control System, or DCS. Now here, instead of one big central controller doing everything, the control functions are distributed among multiple autonomous controllers all throughout the plant. And this makes the system incredibly reliable, because if one controller happens to fail, it doesn't bring the whole operation to a screeching halt. DCS systems are organized in layers, kind of like a chain of command. Way down at the plant floor, you have all the field devices, the sensors and valves. Then, local controllers manage specific zones, like one part of a chemical reaction. And way at the top, supervisory computers give a human operator a bird's-eye view of the whole facility, so they can oversee the process while the individual controllers handle all the nitty-gritty details.
A DCS is absolutely the system of choice for any large, continuous process industry. We're talking massive oil refineries, really complex chemical plants, and pharmaceutical manufacturing facilities. Any place where precise control and super high reliability are non-negotiable.
So we've covered massive areas with SCADA and complex plants with DCS. But what if your entire focus boils down to the ultra-precise movements of just a single machine, like a milling machine or a robotic arm? Well, that is the domain of CNC, which stands for Computer Numerical Control. This is all about controlling the precise motion, position, and speed of a machine tool. It uses a computer to read a program made of these symbolic codes, you might have heard of G-code, and then translates that code into exact physical movements.
The machine control unit is the brain of the operation here. It sends super precise commands to the machine's motors. But here's the really clever part. It also gets feedback from the machine, creating what's called a closed loop. It's constantly checking its own work, asking, did you move to the exact spot I told you to go? And this constant feedback is what guarantees that incredible, repeatable accuracy. Okay, so let's put this all together because this is really the aha moment. The easiest way to remember the difference is with an analogy. Think of SCADA as the air traffic controller, watching over a huge area from a distance. A DCS is like the crew of an aircraft carrier. They're managing a massive, complex, but totally self-contained system. And CNC, that's the surgeon, focused on making incredibly precise, delicate movements. Now these technologies, they've been around for decades, but they are far from being static. They're constantly evolving, getting smarter, faster, and way more connected than ever before. The future really is all about integration. These systems are blending with the Internet of Things. So now a single wind turbine can report on its own health in real time. We're adding AI to the mix to predict when that turbine might fail, letting us schedule maintenance before it breaks. And of course, as everything gets connected to the Internet, robust cybersecurity becomes absolutely critically important to protect our infrastructure.
Which really leaves us with a final thought to chew on. I mean, we've gone from walls of clicking relays to AI-powered cloud-connected networks. The evolution of industrial control has been nothing short of incredible. So as this intelligence just continues to grow and grow, it kind of begs the question, right? Are we heading towards a future where the factories that build our world will, well, eventually just run themselves?